Rahim. Assalamu alaikum, dear students. Welcome to the Electrical Engineering channel. In this lecture, I will discuss span of a vector space. So, the span of a vector space can be defined as the set of all linear combinations of a collection of vectors v1, v2, v3 up to vn from Rn. Okay, so this is called the span of all the vector which are present in the set, right? So, the set of vectors v1, v2 up to vn. So this set denoted by span of all these vectors is always a subspace of Rn. So Rn is the n-dimensional vector of real numbers, and since it is clearly closed under addition and scalar multiplication. If V is equal to span of V1, V2, V3 up to Vn, then V is said to be spanned by V1, V2 up to Vn. Okay, so let's solve some examples. And we are given set of vectors 1, 1, 1, minus 1. So 1, 1 is first vector, 1, minus 1 is the second vector, and we have to check if S spans R square. Okay, R square means a two-dimensional vector of real numbers. Okay, so let's solve this matrix. So 1, 1, 1 minus 1 multiplied by C1, C2, it is equal to xy. Okay, so x is the x-axis, y is the y-axis. So this is two-dimensional plane or xy plane. So C1 plus C2 is equal to x and C1 minus C2 is equal to y. So let's subtract first equation from the second. We will get minus 2 C2 will be equal to y minus x. So this thing can be written as 1, 1 and 0 minus 2. So here we have C1, C2, and here we have x and y minus x. So this is x, this is y minus x. So clearly minus 2 C2 is equal to y minus x. So C2 will be equal to x minus y divided by 2. And we can also evaluate the value of C1, and C1 will be equal to x minus C2 because C1 plus C2 is equal to x. So C1 will be equal to x minus C2. So x minus this is C2, and after simplification we will get C1 equal to x plus y over 2. Since both C1 and C2 contain x and y, it means set S spans the whole R square planes or whole xy plane. Okay, so this is how we can evaluate the span of two vectors. So let's solve another example. And in this example, we are given this matrix, and this matrix also contains two vectors. This is vector 1, this is vector 2. So let's check if this matrix spans whole R2 or a whole XY plane. So here C1 will be equal to X and C2 will be equal to Y after writing this matrix in this form. So C1 will be equal to 1 and X and C2 will be equal to Y. So again, C1 and C2 contains both X and Y axis. It means this matrix spans whole two-dimensional plane or whole XY plane. So let's solve another example, and in this example we are given three vectors and we can write these three vectors in the matrix form. And here we can check that V3 is equal to 4V1 minus 5V2. So here the third vector can be written as the linear combination of first and second vectors, right? So V3 is equal to 4V1 minus 5V2. So it means this set of three vectors doesn't span whole R cube or whole XYZ space because we have three vectors and each vector is actually three-dimensional vector. So we have to check if these three vectors span the whole R3 space, right? R3. R3 means XYZ space because we have three-dimensional vectors. But since one vector is depending on the other two vectors, so it will not span the 3D space. Okay, so this third vector will be wasted, and the span of these three vectors will not be actually 3D space, but it will be 2D plane. So the span of this set v1, v2, v3 will be equal to span of v1 and v2, because one vector is actually depending on the other two vectors. So the span will be equal to R2. We can also check it by performing this algebraic operation. We can multiply the first column by 4 and we can multiply the second column by 5. Okay, and we can subtract them from each other, and we will get the third column, right? So another way of checking this is reducing the matrix. Okay, and we can reduce this matrix to the triangular form. So the triangular form can be achieved by making this entry equal to 0, then this entry can be made equal to 0, and finally this entry can be made equal to 0. Then this matrix will become triangular matrix or upper triangular matrix. So this entry can be made equal to 0 by multiplying the first row by 5 and second row by 2. So the first row will become 10, 5, 15, and this row after multiplying by 2 will become 10, 2, 30. So let's subtract these two rows and we will get 0, 3 minus 15. So 0, 3 minus 15 will be our new second row. Now we have to make this entry equal to 0, and this entry can be made equal to 0 by multiplying the first row by 3 and third row by 2. So the first entries of both rows will be equal to 6, and these entries will also change, and after subtraction we will get 1 minus 5. So 0, 1 minus 5. So here 3R3 is equal to R2, or we can say that the second row is equal to 3 times the third row, right? R2 is equal to 3R3. So we have got a linear combination of two rows. It means the system is linearly dependent. So this implies that the third vector lies in the plane of the other two vectors. So the three vectors do not span the whole R cube space. Instead, they span the plane of any two vectors. That is, span of v1, v2 will be v3 is equal to span of v1, v2, and it is equal to span of v2, v3, and this is equal to the span of v1, v3. So let's solve another example, and we have to evaluate the span of uh, this matrix S. So this matrix is given as set of three vectors v1, v2, v3. v1 is 2, 5, 3, v2 is 1, 1, 1, and v3 is 4, minus 2, 0. And in this case, we don't have any relationship of any vector with the other vectors. So in this case, no vector lies in the plane of other two vectors. So all the three vectors actually lie in different planes. So this is vector v1, this is vector v2, and this is vector v3. So if we make a plane containing v1 and v2, then v3 will not be present in that plane. Similarly, if we make a plane based on vectors v1 and v3, then v2 will not be present in that plane. Similarly, if we make a plane of vectors v2 and v3, then v1 will not be present in that plane. So in this case, the span of these three vectors will be equal to R3. So this is actually the concept of evaluating the span of two or three matrices, two or three vectors. Okay, so let's move to another topic, and that is basis of a vector space. And a set S equal to v1, v2 up to vn of vectors in a vector space V is a basis for V if S spans V and S is linearly independent. If these both conditions are satisfied, then we can say that the set of vectors in vector space V is a basis for V. So if these two conditions are satisfied, and here spanning involves the column space and linear independence involves the null space. So these are the things which we also have observed in our previous lectures. Okay, so spanning involves the column space, and you can see that here we are evaluating the column space. And if we want to check the linear independence, then the same way of writing the linear combination of matrix is adopted. But here at the right hand side, we have the zero vector or the null vector. So that will become the null space. So by null space, we evaluate the linear independence, and by column space, we evaluate the span of vectors. So that is all about our today's lecture on span of a vector space and basis. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.